Hello students, welcome back. Let us resume our discussions on elementary row operations. What are elementary row operations? Here they are. Multiplying a non-zero number to entire row, adding one row to the other, and finally interchanging two rows. And those are elementary row operations. And what are the applications that we have to consider? There are three. One of them we already did. Solving a system of linear equations. So we started from a traditional form and then changed it into vector equation and then reduced it further into augmented matrix, which is just a shorthand of that one as a matter of fact, and then applied elementary row operations multiple times. Eventually we got to some simpler matrix like this. And this kind of matrix is called a row-reduced echelon matrix. What's the key characteristic? Below this principal diagonal, we have all zeros. So that allows us to solve x and y and z with respect to the others, in this case w, which is highlighted in blue, and then the constant term. Indeed, here is the solution. From the first row, we get this equation because y and z are killed, so you can easily get x, y, and z solved out. So that is how we apply the elementary row operations to system of linear equations, but also that's an implication of row-reduced echelon matrix as well, because this is one such example. Row-reduced echelon matrices are not unique. Even from the same matrix system here, you're going to get different elementary, you're going to get different row-reduced echelon matrix. This one, this too is row-reduced echelon matrix. As you can see, we have all zeros in lower left-hand side corner. Principal diagonal, we have ones, and then all these are non-zeros. That's okay. But lower left-hand side corner, they're all zeros. Those are examples of what you call the row-reduced echelon matrices. And then this helps us solving the system. You can rewrite all these, and then you can start from down below. You can solve for z, and then plug those in. You can solve for y, and now plug those y and z in, and finally you can solve for x. So as long as these in lower left-hand side corner, all these are zeros, you can retrieve all those characters with respect to the others. And that kind of thing is called row-reduced echelon matrices. In general, we are looking for something like this, but this is an ideal case. Ideal in a sense that we can embed the identity matrix in there. We saw two examples. If we have identity, then of course computation is simple. We have more zeros. But the other case also worked out fine. The key characteristic was 0 in lower left-hand side corner. Here's another example. This is another example of row-reduced echelon matrix. It was taken from our textbook. Now, this doesn't have anything to do with embedded identity, but lower left-hand side corner, those are all zeros. So you can work this one out too if necessary. So those are row-reduced echelon matrices. Especially when we have square matrix, row-reduced echelon matrix is actually upper triangular because lower left-hand side corner, they're all zeros. So non-zero part is upper triangular part, upper right-hand side part. But those kind of things can get very deep very quickly, so let's move out of here. And just remember one thing, any matrix can be reduced into row-reduced echelon matrix by applying appropriate elementary row operations multiple times. Okay, alright, so much for second application. So much for second application. Let's go to the third application. Elementary row operation matrices. What are those? It'll turn out that elementary row operations corresponds to matrix multiplication. We begin with this. No change if you multiply identity matrix. Clear? Now, How about multiplying a non-zero number to a row? For example, start from the identity, and then change the second number in the second row into -3 and multiply. What does it do? Entire second row times -3. How about the next example? From the identity, it changes fourth row into 1/2. What does it do? Entire fourth row times 1/2. The conclusion: this elementary row operation corresponds to a matrix multiplication to the left. How about something else? Adding one row to the other. Time is running out, so let's do only the second example. So add second row to the fourth row. So we begin with the identity like this. And from this one in second row, we are adding it to fourth row, right? Go down to fourth row and put 1 in there. So this second row will be added to the fourth. Again, what do we have? We have matrix multiplication to the left. This one is interchanging two rows. Start from identity and then first row come down to third row. Third row went up to first row. We have to leave, so these become 0. Anyway, the key point is matrix multiplication to the left. Is that important? Yes. For example, let's go to example problem again. Let's suppose we have a system of linear equation which became a matrix equation, Ax is equal to c, and then we just apply elementary row operations, E1, E2, E3, and so on. They correspond to multiplication to the left. And then to the R application, what do we have? All these matrix multiplication to the left. This one on the right hand side is pretty clear. That corresponds to this C becoming this one by multiplying all those matrices to the left. That was easy. But how about the others? How about this multiplication of these matrices? That is the row-reduced echelon matrix. So row-reduced echelon matrix times the x, so you can solve for those x with respect to other variables. And that's what we did in that example. And this is the proof, the theoretical background. Now, final application is inverse function, or inverse matrix, excuse me. How does it work? We begin with invertible matrix and let us apply elementary row operation E1, E2, E3, and all the way up to ER, and ended up with a row reduced echelon matrix, which happens to be I. Remember, every matrix can be transformed into row reduced echelon matrix through all these series of elementary row operations, but not everything can become identity. But in this case, let's suppose it can become identity. In that case, this part, E1, E2, E2, all the way to ER to the left, is the inverse matrix because this times A is equal to I. Now, how do you find out the inverse matrix? We consider a parallel process, from A to E1A, at the same time from I to E1I, and then multiply E2, multiply E2, multiply E3, multiply E3, all the way up to ER, then A times all those becoming I, but I times all those will become this very expression E1 through ER to the left, and that is the inverse function we are looking for. So this is a theoretical background of using elementary row operations to find out the inverse matrix. How do we actually do that with concrete examples? We are going to do that in a separate video. Here, in this video, let's talk about only the theory part. Okay, we are done about the half of the length of the usual videos.